Welcome to the Explainer. When you stand at the base of a massive mountain, it feels completely eternal, right? Like it's just this unmoving, permanent fixture of the Earth. But honestly, that's an illusion. Today, we're unpacking tectonic genesis. We're talking about the incredibly dramatic, unstoppable, and agonizingly slow-motion violence that literally reshapes the Earth's crust.
Okay, think about this for a second. How do solid rock layers actually bend? I mean, if you try to bend a piece of solid rock, like a chunk of granite or limestone, it shatters, it just snaps. Yet when we look at mountainsides, we see these huge sweeping ribbons of solid rock weaving and looping around like soft clay. So how on earth can rigid solid rock behave like that? Well, the answer lies in the incredible, almost unimaginable forces of tectonic plate movement acting over vast spans of time, all combined with intense heat and pressure deep underground.
So we're going to break this massive geological journey into 4 distinct steps. Step 1, plates collide. Step 2, rocks compress. Step 3, folds form. And Step 4, mountains rise.
All right, let's jump right into Section 1, the collision course.
So, the Earth's crust isn't just one solid shell. It's actually cracked into these giant puzzle pieces called tectonic plates, and they are constantly surfing on top of the planet's semi-fluid mantle. Our trigger for mountain building begins when 2 massive continental plates drift onto an inescapable collision course. We are talking about millions of square miles of solid landmass moving horizontally toward one another. And they aren't moving fast, maybe just a few centimeters a year, which is basically the speed your fingernails grow. But the momentum behind them, it's practically infinite. When these 2 behemoths finally meet, absolutely neither one wants to give way.
Moving right along to Section 2, trapped under pressure.
This is where we introduce the protagonist of our geological story, and that's the seemingly innocent, flat layers of sedimentary rock. Imagine the space between these 2 approaching continental plates. Often, this area was once a shallow sea, or maybe a massive basin, just quietly collecting colorful horizontal layers of sand, mud, and organic material for literally millions of years. Over time, those layers hardened into sedimentary rock. But now, enormous forces begin to compress the Earth's crust. Those quietly resting layers of rock are suddenly trapped. It's like they're caught in the middle of a planetary vice grip. As the continental plates continue their aggressive approach, the millions of tons of pressure building up on these trapped rocks is just absolute and relentless. They are being squeezed from both sides, and there is nowhere for them to escape.
Which brings us to Section 3, bending the Earth.
Under this incredibly intense pressure, the horizontal rock layers begin to bend and fold. Remember our question from earlier about how rock can actually bend without breaking? Well, because this compression is happening super deep within the crust, where temperatures are really high, and because the pressure is applied incredibly slowly over millions of years, the rigid rock actually loses its brittleness. It becomes ductile. Basically, it just can't stay flat anymore if it's going to survive the immense strain. So instead of snapping, the tremendous horizontal compression forces the once flat sedimentary layers to buckle. They warp upward and downward in these massive slow-motion waves.
Now, as these rocks fold, they form very specific geological structures. The first one is called an anticline. This is an upward arching fold in the rock layers caused by that intense compression. Think of it kind of like the shape of a giant capital letter A. The rock layers have been squeezed so hard from the sides that the middle has been pushed right up into a distinct arch-like curve.
And immediately accompanying the anticline is its structural partner, the syncline. A syncline is a downward dipping trough or fold in the rock layers, again resulting from that exact same crustal compression. If the anticline is the crest of a wave, the syncline is the valley or the trough sitting right next to it. They're shaped somewhat like a giant letter U or V just dipping straight into the earth.
Thinking about anticlines and synclines side by side brilliantly illustrates the whole dynamic relationship here. You can clearly grasp how the Earth's crust effectively ripples. I mean, it is literally behaving like a rug that you've just pushed together from both ends. The fabric scrunches up, creating hills and valleys, right? Well, this is exactly what the sedimentary rock is doing, just on a scale of kilometers. These continuous sequences of anticlines and synclines are the literal architectural foundation of fold mountains.
But here's the catch. The continental plates don't just stop once a few folds are made, they keep pushing. So as compression continues, these folded rocks are pushed violently upward. With the tectonic plates continuously crushing inward, the buckled rock simply runs out of horizontal room. The only direction left to go is up. This is the release of all that unimaginable tension. The massive accordion-like layers of rock are thrust higher and higher, completely defying gravity.
breaking right through the surface and reaching for the sky.
Let's ground this in the real world with Section 4, Famous Fold Mountains.
But before we name drop, we need to focus on this one crucial number: millions. You can't exactly set up a time-lapse camera for this over a long weekend. It takes millions of years of continuous, agonizingly slow upward thrust to create the mature mountain ranges we know today. What starts as just a subtle warping of rock deep underground, eventually, after millions of years of tectonic pressure and surface erosion, becomes those towering, steep ridges and deep valleys that define a classic mountain landscape.
The most iconic, absolutely breathtaking mountain ranges on our globe are the direct result of exactly what we've just learned. Take the Himalayas, for example. They were formed, and actually are still being formed, by the Indian plate smashing into the Eurasian plate. The Alps in Europe, that's a product of the African and Eurasian plates colliding. And the Andes in South America are just another spectacular example of tectonic folding and uplift. When you look at these mountains, you aren't just looking at rocks. You are looking at the crushed, folded, and uplifted remnants of ancient seabeds, pushed way up into the sky by the sheer force of moving continents. It's absolutely wild.
Which brings us to our final thought for this explainer. The Earth's crust is still shifting today. The plates haven't stopped moving. The Himalayas are actually still growing taller by a few millimeters every single year because that tectonic collision is ongoing right now. It really makes you wonder as you look out at the landscape today, what future mountains are being built right beneath our feet? The flat plains or the deep oceans of today could very well be the snow-capped peaks of tomorrow's world. Thank you so much for joining me in breaking down the fascinating origins of fold mountains. Keep looking at the horizon, and I'll catch you on the next one.